Good afternoon, everyone. Welcome to our second webinar in this series on environmental management, funded through an educational and training grant from the National Endowment for the Humanities. These webinars are designed for institutions who are in the initial stages of implementing the environmental management. Those of you who currently have data loggers in place or in place with less than a year's worth of data. There we go. Sorry about that. We're coming to you today from IPI. The Image Permanence Institute started in 1985, studying film and photographic materials and seeing the importance of environmental conditions on preservation. We expanded our scope to address the concern for these materials into the mechanical environment. Your presenters today are myself, Christopher Cameron, Sustainable Preservation Specialist, and my co-presenter is Kelly Krish, Preventive Conservation Specialist. We encourage you to ask questions as they come up, which you can do by typing in the chat box. That you'll see on your screen. This webinar is also being recorded, so if you have any questions, if you're watching this in the future and something comes up, please feel free to use the email on the previous page, post any questions to us, ask any questions you may have or concerns. Also, please take the time to fill out the survey that will come up after the webinar. We do take the feedback and we evaluate it and use it to strengthen our educational resources for the future. Environmental management is a process with multiple phases. Last webinar, we covered the topics that are grayed out, as well as began discussion of some of the others. Today, we're going to begin addressing some of the remaining pieces. So assembling our documentation, we want you to gather the information about your building, the blueprints you have, walking through the spaces, evaluating your collections, having conversations with staff. There are some forms that we've created to help track a lot of this information. These forms are available in the Implementing Sustainable Energy Saving Strategies, which is available on the IPI Sustainability link under the Resources tab. So the last webinar, we discussed risk assessment from the perspective of the 10 agents of deterioration and object vulnerability, exposure, and likelihood. Now we look at features of those levels of control that could contribute to deterioration and inform our analysis of environmental data. So last webinar, we were here in the object level, and we're going to be moving up to the location, site, building, and room perspectives. So we want you to keep in mind, the type of building you have or the room design will have a significant impact on the environment you are capable of producing. Buildings that are open structures, have little insulation or single glazed windows will be less capable of holding an environmental condition compared to modern metal and concrete frames that have tight construction, tight insulation, tight vapor barriers, those types of things. Within the building, the room design will matter as well for the same exact reasons. Holes in the walls, missing or propped open doors, poor insulation or vapor barriers are also going to play a part in the collection environment. One of the best examples I can give to this is more recently we have seen an influx of people that are attempting to turn loading docks on their building into cold storage, and just a cinder block room with a garage door, and they've modified them slightly in some circumstances or not at all, and they tend to put essentially an air conditioning unit in the room and try and make it work. And we've noticed that, without the proper insulation, without vapor barrier, even the appropriate ceiling or unit, these units tend to spend a fair amount of energy because the room was never designed to hold those conditions. So there are three primary types of collection spaces: exhibition spaces, storage areas, and cold storage. Each one of these will come with their own settings, their own set points that they'll require, and many issues that they'll require as well. Your exhibition spaces are going to primarily be human comfort. You're going to have a lot of occupancy in them from people coming in to look at the collection. So your aim is going to be more for human comfort than collections. Your storage areas, your collections are going to need cooler temperatures. So while you may want to achieve those cooler temperatures, there's dependencies on, do you have staff that work in the space? Do you have, what types of collections you may have? Is your building capable of holding those collections? And cold storage, again, to my statement earlier, you're trying to make cold storage, is your space even capable of holding that as well for the temperatures you're trying to achieve? And it all starts here. Your mechanical system is the major piece of your system. This is the main, this is where your environment is created, right here. Knowing how your system is laid out, what it's capable of, and the areas it serves is incredibly important. We do not expect people to be trained HVAC technicians, but we do hope that you'll learn how the system affects you, how it affects your collections, and how it creates the environment your collection lives in. We want you to build an understanding that your HVAC, we want you to build an understanding of your HVAC system and how it creates the air that flows through your space. Not all of you are going to have an air handling unit. Some of you may only have boilers in your collection space. Some of you may only have forced air systems. So depending on what you have, we want you to understand what that system does to create the space. How does, how the system works. And again, there's some guides to walk you through a lot of this in that the implementing energy saving strategies, which again, we'll have available. We'll have the link at the end of the webinar for that. So going inside a unit, we're not going to cover all parts of the unit. Just want to give some brief sections of some of the units, what you may have, and what they'll do to create that environment. So if you go open a unit, even an air conditioning unit has a cooling coil. So your coils will generally look the same. If you look at them, a heating coil, cooling coil, similar in design with the fins and the tubes and the fins. And it's just, helping to identify what they are, what they do. Your cooling coil is going to just do just that. It's going to cool the air as it passes. If possible, it will dehumidify. That's dependent on the dew point of the air passing over the coil and the capabilities of the coil. Not every cooling coil will dehumidify all the time. One way to identify a cooling coil, if you're looking in here, is via the condensate tray, which is underneath the coil. It's to catch the water if it condenses and rush it out, remove it from the unit. And then there is your heating coil, which would be the image on the left, on the right. Again, that's a tube and fin, but they can also come in electric style, which would be similar to a toaster heating coil, which would run back and forth across the airstream. And obviously the heating coil would have no condensate tray. So some downstream equipment you may have, and we refer to as downstream equipment, but they could be inside a unit. They could be located somewhere in a ductwork or even inside your collection space. Some humidifiers and reheats. Humidifier is obviously the piece of unit that adds moisture to the air passing. It's going to increase your RH level. And if you look, it'll be identified usually either by tubes right here with the holes in it, or there are also maybe some spray nozzles. If you can't look inside the ductwork, you could look for some signs. This is actually a reheat with a humidifier, so you can see the water lines going to it with this little canister here. And if you can open up sometimes they're inside a cabinet, so there'd be a canister as well. Just to give you an idea, if you have humidification, and the reheats are designed to reheat or tweak the air leaving an air handling unit to try and reach an optimal temperature. So reheats are generally designed per space for a unit, and that'll help you just get that air to a specific temperature. A couple issues may happen with these. We've seen them leak. The source of water, especially in your collection space, if they break, can cause an issue, or failure could result in lack of heat or humidification downstream. So when we were working on creating this series, we asked a question and asked, does anyone have any questions or what they would like to learn? One question we had would be to identify the difference between supply vents or diffusers, or supply vents or diffusers, or return vents. So we'll just take a brief sample of that. So there's no general difference in design of supply vents. I've seen them come in just about every shape, size, design you can ask for. From round to square, I've seen them 3 inches wide to 2 feet wide. Things to look for if you're trying to identify it, can be some directional vanes coming off, or even inside a style like this, they'd be right inside the face of it, or sometimes dampers to help shut the airflow down. This one on the lower bottom is actually a trick. It is a light fixture that, if you see the blue arrow going to it right here, is a light. It's a 4 foot by 4 foot square light fixture with the supply air around the outside of the fixture. So return vents are, it's the same as supply vents. There's no design specification for them. They come in all shapes and sizes as well. There are a few things to look for with them. They do not have directional vanes normally. Normally, not all of them have dampers on them as well. General rule, a general rule it can be is at times they don't need ductwork. If you were to look over this type ceiling tile right here, it just opened up into the ceiling and returned back to the units. A lot of all supply ducts need at least the ductwork going to them. In general, there tends to be less returns than supplies. So if you're in a space, you have 3 grills of one type and 1 grill of another. Most likely the 3 are the supply and the 1 grill is the return. And these last 2 are examples. This one circled in red is a large 6 foot by 6 foot square return that served an entire building, while this blue one is what I was talking about, the open plenum where it pulled into the ceiling. That was just to get give an example of what it looks like up in the ceiling. There were the round vents to pull the air trapped up there back into the unit. If you do not know which area your supply returns, there's a few ways for you to identify. You can look on your blueprints for your mechanical system, and usually tracing those out with a pen or so or a marker will help you identify, am I looking at supply or return? If you don't have your blueprints, some individuals have actually walked their space and just traced them out by eye. And if all else fails, if sometimes the ducts go through the wall and you can't trace them, a good option just to identify what our supply or returns is using a basic tissue. A simple tissue test is an easy way to check airflow. Recommended over, some people have suggested a piece of paper, but we've seen airflow so small that it doesn't even move a piece of paper. Generally, the tissue will move one way or the other. But using that tissue will help. There are times when even Kelly and I are looking at facilities and the air is so small, you hold it up, and if you hold the tissue up to a supply vent, it'll blow away from it. If you hold it up to a return, it'll be pulled up towards it. So a few issues that we see while we're talking about supply and return vents. I will say that the first image on the far left is one over here is one that almost everyone that's listening probably is responsible for. You probably have this going on in your building. Of all the facilities we worked with, I can only think of maybe 2 or 3 that didn't do this at least in one location of their building. Putting boxes or items or objects too close to the supply or the return vents. On the return side, you can starve your unit of air. Air will not get to the unit. It'll impede the air flow and cause the unit to run inefficiently. If you, for the supply side, if you put boxes too close in front of the supply diffuser, less than 12 to 18 inches, there is a possibility the air will not mix properly when it comes out of the vent. And in coming out of the vent, if you lose by chance a reheat or the heating coil may go down, there is a possibility where you could have air that's very cool with a high moisture content blowing right on your collection materials. And we've seen instances where that has caused mold on a collection. We'll give an example of that in a few slides. Another incident is, if you look at this longer image on the far right, you'll see supply, return, supply, return, supply, return, all down a line. What happens in a scenario like this, the air will be exhausted from the supply vent, and almost immediately half of that air will be drawn right back into a return vent. A lot of that air isn't making it right into the collection space, conditioning the space at all, and we refer to that as short circuiting, because a lot of the air is coming right out and just going right back to the unit. And third image, the middle image, it's a little harder to identify, but here is, we used an infrared camera walking through when we evaluate a space, and we were able to identify both ducts coming from one air handling unit where one was heating and one was cooling. And in a scenario like this, we wind up having the system is fighting itself, trying to create a condition to compensate for the lack of heating on the other vent. So your thermostats. A thermostat is a key piece of your mechanical system. The thermostat observes the condition in your space and tells your mechanical system what to do, regardless of the type of system you have. Even if you have a basic boiler in your facility, it's got to be controlled by one element, which would be a thermostat located somewhere. Again, like your supply and return vents, they come in variety of shapes, sizes, some with screens, some with buttons. Best rules to identify a location. They're usually located between eye to chest height on a wall, and they are generally kept away from sources of heating or cooling, like away from windows or doors, something that may trick the thermostat. And that being said, when you're organizing a room or a space, please keep errant sources of heat away from thermostats. As a facility manager, when I was working as a facility manager, the amount of times I would go to investigate a heating or cooling issue and found coffee makers or computers directly under thermostats, and the heat that comes off of that unit would trick the thermostat, causing another issue. So make sure you keep a lot of those, anything that would put a source of heat near the thermostat away. And most importantly for thermostats, please keep airflow. Just like we discussed with the supply diffusers, give them about 12 inches at least. Let the air mix freely around thermostats. We tend to see this quite often, and sometimes we've heard it's unavoidable. We're putting shelving up, whatever. But blocking thermostats can lead to severe inefficiency with an HVAC system. Using the image on the right, for example, say this is an outside wall that thermostat's on. That interstitial space between the thermostat and the wall could be in the wintertime, say the wall is cold, so you have a cold pocket of air. The air doesn't mix with the room air, so you wind up, again, the thermostat's going to see that cold condition, believe it's cold, even though the room may be slightly different. So in response to the cold the thermostat sees, it will begin to heat the space. So you may walk in and notice the room warmer than normal, and it could be a result of a trapped thermostat being misled. And then you start making adjustments to the system, and in making those adjustments, it just further goes down the rabbit hole because that thermostat is trapped. And actually the image to the right is a thermostat that was behind a workstation built in a collection space that actually took us quite a while to find. And remember, as I said earlier, these will lead to pretty inefficient HVAC operations. The last item I can discuss, I'll discuss for mechanical systems, are the standalone radiators. Some of you, these may be all you have in your collection space. You don't not all of us do have HVAC systems that you may just have these radiators. They're designed to what we call wash outside walls or window surfaces with warm air. They come in the two styles, either water or electric. You can identify if it's water, most likely we'll have steam or water pipes going directly to them, or if it's electric, we'll have an electric line going to it. And I was asked to identify that this black mark you see above this heater is actually from an operation of the object. The heater was firing much hotter than it should have been, not to the point of causing a fire, but to the point of actually leaving the black marks along the walls and on the unit. Other inefficient operation we tend to see with these radiators are they run, not all, every now and then we'll work with a facility that we'll see one working more than it should. We'll go into a facility in the middle of summer and open a closet or a storage room that has one of these radiators in it, and it's just running. And it tends to be, especially sometimes it happens with electric ones, it can be quite energy costly to run them when they don't need to run, especially summertime. So a couple of helpful tools I'll go over. Number one helpful tool that we use when we're doing these walking through spaces is a non-contact digital laser infrared thermometer. And it's a mouthful to say, but the layman's terms is just a temperature gun. They're pretty cheap. They're pretty, you can pick one up for anywhere from around $150 to $100. Definitely recommend having one if you're walking through a collection space. They're excellent for spot checking, walking around like here, that's actually me spot checking a radiator, checking supply return diffusers to see what the temperatures are on them, cold spots on walls, things like that. Definitely recommend having one, using one as you walk through your collection space too. Just even, like I said, just spot checking things. The next object many people might not have thought of using is an infrared camera. Some people would balk at the thought of it because in the past they've been incredibly expensive. Standard infrared cameras a few years ago would run in the thousands of dollars. They've actually, a lot of technology has gone into making these things very small and very affordable. You can get smaller, small infrared cameras that plug in the bottom of Android or Apple phones now, and they cost about $100. There are now infrared cameras that are simple, about the size of a cell phone, which is what we use to take an image of the system on the right. They run about $400 to $500. Definitely recommend if you're going through your collection, if you're assessing the space using one. These two images here, the one image on the right is what you saw walking through the space, just what you observed in the collection space. The image on the left is what we saw in the collection space. I apologize. The image on the right was what we saw as we imaged everything with the infrared camera. And though the space was close to temperature, what we saw as we looked through the space is a reheat had failed, and every other vent in the space was served by that one reheat. And they were all, one side of the air handling unit was supplying cold air and the other side was supplying warm air. So the unit was literally fighting itself to make the condition for that room. So lastly, one of the other things we were able to use this for is we worked with the museum a few years ago, and we went into their lobby, and their greatest concern was they could never get their lobby to temperature or to a cool temperature. It was always in the wintertime very hot, uncomfortable, to the point where they almost shut the air handling unit down. And we started imaging the space, and lo and behold, using the infrared camera, you could see through the floor the outline of the boilers. So all that heat from the boiler that was heating the space was coming straight up through the floor and warming the room above. One of the last tools I'll talk about today is creating a zone map for your collection space. Once you get a basic understanding of your system, you should understand the spaces it serves. It helps you understand exactly what this mechanical system is doing. Do you have one unit serving two spaces? Do you have, so here, we have this blue unit serves one, this purple unit serves one, and then this front room is served by 2 units. The print on the side, one unit has 3 zones off of it that serve one very large space. So it gives you an understanding. How is my collection, how my space is handled? So when you understand that there's some zoning issues that you can identify. One unit serving multiple collection spaces, forgive me for going back, but one unit serving multiple collection spaces, I'll use this image with the green and the red here. If you look at this RTU1, say, it's along a window area, it may be running cold, the windows may be cold in the wintertime, so that unit may be heating a lot to make up for the cold, as I said, washing the window area with some warm air. In response, because it's a large room, the thermostat for RTU2 may see some of that heat and to compensate by dumping some cold air in to make up for it. So you may wind up in a scenario where the 2 units will fight each other to create that condition. Same can be said in a similar scenario for this room, where we have 3 zones from one unit. Say this zone 1, this large green zone, were to fail. If that zone fails, then we'll have cold air coming out in that zone. If the reheat fails, we'll have cold air come out in that zone. So the blue and the yellow zones on either side will have to compensate and therefore push really warm air in. So the unit's going to work hard on 2 ends to make up for the middle not working. So you can wind up with inefficient operation on those ends as well. Lastly, if we have one air handling unit serving spaces occupied by collections and staff, we very much recommend, if it's possible, to keep those spaces as separate as possible. We have in many instances seen almost all of these collection spaces served by directors, restrooms, galleries. They come with a very major drawback. Human comfort issue is a big problem. You're trying to condition a collection space at the same time you're trying to condition for human comfort. Collections need cool conditions, and when you condition for human comfort, you're conditioning for a whole different atmosphere. The addition of even one staff member occupying a collection space long-term will change the condition, and the presence of that one person will result in the needs for the human comfort rather than creating the quality preservation environment.
Okay, so hopefully that gives you a good sense of some of the information that can be helpful in environmental management, aside from just our traditional data logger data. So we've reviewed some of the information related to collections to see the needs in the previous webinar, and then just now we've gone over the building and the mechanical system to demonstrate some of the challenges and start to define what options we might have in place through that information gathering. The zone maps are meant to show too how they all kind of come together, similar to how we talked about overlaying risks. And we can start to see potential issues if we make changes, even before we get a sense of what the data itself is showing. So now I'd like to return to defining the objective and some initial data analysis. We did talk briefly about defining the objective in the previous webinar when we discussed answering general versus specific questions. So here we're going to go a little bit more in depth in terms of both of these aspects as they relate to sustainability. So this is a slide we've seen before, and we're going to look towards that optimization first with two strategies that make good starting points from both a preservation and a sustainability perspective. And that is to eliminate extremes and focus on harmful microclimates. So for extremes, this is often more of an issue if temperatures or humidity are higher rather than low, given the related deterioration issues that we discussed previously about regarding each one. It's also important to mention here in our discussion of extremes that long-term trends generally matter more than short fluctuations over the lifespan of a material. It can be very disconcerting to come back from one night and see a spike in relative humidity that's then returned to normal, or just, over a weekend, maybe there was a system failure and conditions climbed rapidly. And sometimes these can be a concern, but often what we're looking at even more so is, are we maintaining high levels over long periods of time? Do we keep that humidity high all summer versus just, maybe for a day or so? So, and these extremes are often present in areas where we either don't have control or don't have as much control as we'd like to have. It can also be in areas with additional loads. So, if it's a space that happens to have natural sunlight coming in as well, we have a solar load that's not accounted for in the rest of the spaces. There could be adjacent areas such as atriums or kitchens that are adding to heat and moisture loads within a certain space that aren't present throughout the whole collection area. And as well, it can also be due to changes in operation. Sometimes a set point is changed intentionally or unintentionally, and sometimes it's a matter of a set point not being changed back at the end of, maybe you're using seasonal set points and things didn't quite get changed over in time between winter and summer operations. The ways to identify these, first and foremost, staff that work in collection spaces are often very familiar with which areas of a room or which rooms tend to be hotter or colder or feel damp. Maybe the air is more still, things like that. So reports from the people who are working within the collection space can often give you an initial sense of where those extremes are located. We can also use the temperature gun and the infrared camera, as Chris mentioned earlier, to do spot checks, either with the temperature gun for specific locations or the IR camera to get a sense of the larger area as a whole. And these can point to areas where conditions might be, it's going to show you areas where conditions are different from each other. And then as we start to collect data, we're also going to have this environmental data to back up what we see as extreme conditions, either at certain times of the year or within certain collection spaces. Okay, the consequences, of course, when we talked about higher temperatures, we looked at how that can accelerate the chemical deterioration or natural aging. And we also talked about how we can see an increased risk of other forms of damage. So with, for example, relative humidity, we can see higher risks of mold germination, metal corrosion, and mechanical damage, as well as seeing higher risks from pest activity and increasing consequences from things like light and pollution. There's also operational costs for every additional temperature or moisture load that we put into a space that we want to remove. We're going to have to do so often mechanically, and so that's going to come at a cost, even if it's not either energy or preservation wise. The mitigation or the way that we would combat these extremes is going to depend on the context. So we tried to pull out a few examples of things that would work for a variety of places, regardless of what type of structure you have or mechanical system that may or may not be present. So these, like I said, does heavily depend on context, but these are some of the places where you might start looking to address your extremes. Often the building and room envelopes, those can be letting in some of those extreme conditions from surrounding spaces, including the outside. We can look at reducing moisture loads, either on a building-wide level through landscaping, keeping moisture out of basements, things like that. And we can also look at it from a mechanical perspective of reducing the amount of outside air we use when that moisture is when it's particularly humid outside. We can reduce our heating and cooling loads. As Chris mentioned, often removing occupancy is key to this, especially for reducing the heating loads, just because people tend to add, there's equipment, there's additional changes in operation that are going to add to that heating load. We can reduce our lighting levels, and we can use shades and things like that to help block the heat from actually entering the space to begin with. And finally, we can relocate or buffer sensitive materials. So if we know that we have an area in our exhibit space that just happens to have really high temperatures, it's located in a very sunny spot or something like that, and we're not going to be blocking those windows, we can look at either moving the object or maybe we can, if the humidity is an issue, we can use a desiccant or something like that in the case to help buffer conditions. And you'll notice that a lot of these, again, relate back to those levels of control that we had talked about in both the previous webinar and at the start of this as well. Okay, moving on to harmful microclimates. Microclimates are areas that experience different environmental conditions than the space as a whole. Sometimes they can be good or bad. In just the previous slide, we talked about a good example of a microclimate where we might be purposely using a desiccant to create an area with lower relative humidity to improve preservation. But for this particular talk, we're going to be focused on harmful microclimates. In these cases, they can be along exterior walls or near windows, maybe where conditioned air enters a space. But some of the most harmful microclimates we see are essentially anywhere where a cold surface could lead to condensation or there's a lack of airflow. Inside compact shelving or containers, these kind of places can trap moisture. And in this photograph here, you can see there's some windows. So that's going to be adding additional heat load to the books on the adjacent shelf that aren't really present anywhere else within the collection. We know from previously that if we're increasing those temperatures, we could be reducing humidity. So, there can be consequences to having this, specific areas of the collection space that are being that are operating differently than the whole. So again, we're looking at this as a way of the way to identify these, also very similar to how we approach extremes. But in this case, we're also adding anemometers and moisture meters. The anemometer, if you're not familiar with it, is the tool with the orange case and the fan attached to it. So it's used to measure airflow. Usually microclimates are a result of the conditioned air not quite getting to a certain corner or area of the collection space. So we can use this tool to measure and see what the airflow rates are. And moisture meters can be helpful in terms of determining if the building materials or the collection materials might have higher levels of moisture than what's seen in the rest of the collection space. Okay, again, for consequences, since we mentioned that by and large, what we see in the field in terms of a harmful microclimate has to do with slightly cooler temperatures and higher humidity. One of the main consequences we see from microclimates is that mold outbreaks can occur. And here you can see in the images on the right, there's a supply diffuser there. It's probably trying to cool the space, and so it's probably putting out, cooler air with higher humidity than what would be in the rest of the space. And we have a collection object directly underneath, so that air is coming in contact with the object before it has a chance to mix with the rest of the air and kind of come to a average condition. And so that leads to you can see the white on the violin neck here, and so that's a sign of mold germination. Just like with extremes, we also have increased risks of other forms of damage, and we have the operational costs as well. Mitigation, again, it's going to depend on the context. One of the main strategies, as we mentioned, since it often has to do with a lack of being able to bring conditioned air to a certain part of the space, is to really make sure that we're promoting air mixing, to make sure that boxes and storage furniture aren't blocking supply diffusers or are just really trapping the air between spaces. We can identify and eliminate sources of dampness really at any level. Like I said, making sure that water stays out of the basement, we don't have leaks within walls, things like that. And we can relocate or buffer sensitive materials as we talked about before. All right, so now we're going to look a little bit, we're going to look at some initial data analysis and take into account how the local climate, the building envelope, and the mechanical system can be approached from a sustainability perspective. Okay, so as we're early on in our environmental management, this is some of the first steps you might want to take in looking at your data. I'll say that this is just an example, put up the outside air data for Rochester, New York, where the Image Permanence Institute is located. And we've kind of put up some limit lines here, the bars you see going across the graph that just kind of demonstrate what our conditions for a storage space might be. So we're looking at our local climate data and we want to compare it to our desired storage environment. And this is with the intent of getting a sense of what and when your challenges will be. For us here, we do occasionally experience high temperatures in the summer, and we can also see that we're going to have higher levels of moisture than we want in the winter, or in the summer as well. So we're going to need to dehumidify to some extent. So, this may be similar for you, may be different. You may have wild swings in the shoulder season that might represent your biggest challenges. You might have high temperatures throughout the year. So you're going to want to look at all three parameters, temperature year-round, relative humidity in the winter, and dew point in the summer to get a sense of what and when those challenges are. We're also going to then compare that outdoor environment to the building envelope. Especially if you don't have any mechanical systems, this is just going to be a very clear picture of what that building envelope alone is able to do. It's similar to on a sunny day, if you step underneath the shade of a tree, you can immediately feel a difference in conditions. So really, most types of building envelopes are going to provide some kind of buffering capacity against those outdoor conditions. And in this data, we can see that that is indeed the case. The teal lines represent the outdoor conditions, and the blue and red represent a collection space within the building envelope. So you can see that while it's generally following the trends, it's not experiencing the same extremes, especially on a daily occurrence. So that's the influence of the building envelope. If your building is not as well sealed, it might be following those more closely, and if it's very well sealed, it might not be even experiencing it to quite the same extreme. So for looking at building envelopes, we especially want to look at temperature and dew point to see how it's able to help us out. Okay, if you do have a mechanical system though, we definitely want to document this. Not only does it allow for realistic goal settings, but it also helps us to uncover malfunctions or just inefficient operation. So you can see here a couple of examples for temperature. So the blue line, which is in that remaining white space there, is the temperature of a storage space. And then the red lines represent the conditions outside. So when the outside temperatures are lower than the conditions in the space, we're going to be heating. And when the red lines are higher than the conditions within a space, we're going to need to cool. So this gives you a sense, in this particular example, it looks like most of the time we're going to be heating rather than cooling. When we look at dew point, again, we have this blue line that represents the collection space and the red lines represent the outdoor environment. And we can see that when the dew point is greater outside than it is inside, we're going to want to dehumidify that air before introducing it to the collection space. And when we have humidity levels that are below what we would like in a collection space, we're going to start looking at humidification options. It's also possible that that sometimes the data you look at is not attributable to intentional work being done by the mechanical system, but can be a result of loads on or in the space. This is one that we see very often, and you can see that it's a pretty consistent pattern where that's very much tied to someone's work schedule. So someone's coming into the space, they're probably turning on the lights, they might be propping open the door to allow for easy access or to talk with colleagues, or even opening up shades to make their work environment more pleasant. But here we're seeing that temperature gain for 5 days a week, and we see it drop back down overnight as well as on weekends. So this is why it's important to critically examine the spaces to kind of inform what we're seeing in the data, that this isn't a mechanical system issue, that this has to do with the operation of the space itself. Okay, we're going to go on now to back to kind of looking at the whole picture. Now that we might have a sense of what we're looking at within the data, and from the information we've gathered, we want to start to build that team even stronger, to look at the to really build our environmental management program and start looking at what options we have for improving it. So this is just a possible list of people that might be present on a team. For each institution, it might vary. Maybe there's people that you would add or that you don't have that are represented on this list. So it's just important to consider who your stakeholders are within this. There are many resources to consult to brainstorm options for mitigating risks, but when you're coming up with an appropriate mitigation measure for a specific place, it's often a matter of working with a team familiar with the situation to get input and weighing the options at each of these levels. So the more direct experience that the team members have with the specific context, the more input they can have in terms of unique perspectives on how it might impact different aspects of the operation of the institution and what those consequences might be. So I know from our registration survey that many of you do involve staff from multiple departments in your environmental management. For those of you who don't, we've covered this a little bit before, but hopefully, this will be a good opportunity for things to change. And creating that culture of collaboration will really serve the institution well throughout the environmental management process. Okay, so we collected data in order to identify risks, determine the system's capabilities and malfunctions, and document our needs for improvement. But there's no point in going through these exercises if we can't ultimately do something about the results. So here we're going to move into risk management or mitigation, which refers to reducing the magnitude of the risk. There's both the levels of control, which we've covered in both the previous webinar as well as this one, and methods of control for each agent of deterioration. So each level can be matched with each method, so it doesn't necessarily have to go directly across from list to list, but you can kind of think of examples for each one to match up with the corresponding list. So it can be kind of a helpful framework for going over what your options might be to address each concern. Here we're just going to run through some examples just to give you a sense of how this can come into play. But let's say we want to start off here. We can seal and insulate a building appropriately so that we're blocking those additional heat and moisture loads from entering the structure. We can make sure that we're not heating more than we need to. So this is our mechanical system in on the first floor of our building here. And if we don't heat, especially in winter or during times when occupancy is low, we're not introducing that accelerated risk of damage into the collections. We can use data loggers within our storage cabinets here to detect problems early on. And we can relocate objects that are either likely to be at a risk or already showing signs of damage and place them in a more appropriate storage location. For example, maybe cold storage in our chest freezer shown here if that is appropriate. So after we've kind of have used this framework to brainstorm what our options are, we need to talk about each one in terms of its practicality. So some of the factors that are going to come into account there are time frame, cost, and impact. Certainly we want to do so in ways that also make sense with other options so that we're not later having to counter those effects. So for example, if you don't want to implement a measure that then gets countered by subsequent steps. And we definitely want to make sure that we are working towards the institution's goals and priorities and working within part of that preservation plan. So there's a lot of options that need to be taken, that each need to be weighed with a variety of factors. And again, that's why we stress working with the team so much, that it's unlikely that any one person is going to have all the information needed to fill in these blank questions. Okay, so now we're going to move into some of the actions that can be taken. Again, since we're at the initial steps, we want to make sure that we're taking the actions that we take are appropriate. So again, this is a slide from the beginning. All of the initial steps that we talked about should be doable at this stage. And then there's other things that we want to make sure to avoid. So we've talked a little bit about this throughout the webinar, but certainly lowering temperatures either through set point changes or through window AC units, this can, if we don't have an understanding of how that might affect relative humidity levels through the dew point, this can cause problems later on. We looked at some examples of we've talked quite a bit actually about the risk of mold germination and accelerated metal corrosion and all of those things. So we want to make sure that if we do lower temperatures, we have a sense of how that's going to impact the, how that's going to play through the dew point and impact the relative humidity as well. The bottom two examples are ones that are strategies that are often recommended from an energy sustainability perspective, but are not always appropriate in a collections environment. So the use of more outside air can, depending on when that outside air is being introduced, can sometimes come with additional temperature and humidity loads that the mechanical system may not be entirely able to compensate for. And that's going to be introduced directly into your collection space. The 5-degree temperature deadband, again, that allows for the more flexibility in when the system has to operate, but the consequence in terms of relative humidity can be, about 8%. So depending, if we're already in the upper limits of relative humidity before we're seeing some of those risks, we may not want to add an additional 8% on top of that. Okay, so just our final topic for today's webinar and the webinar series is advocacy. While this does kind of come into play with instituting actions, we also wanted to cover it because so many of you expressed that this was the greatest challenge in starting a program. If you're in that group, you're certainly not alone. The Heritage Health Index found that the most urgent preservation need at U.S. collecting institutions is environmental control. So I'm going to share some ideas that we've seen work in the past or that I've heard about from others. But if people have experiences, good success stories in advocating for preventive conservation or environmental management, we certainly encourage them to share their experiences as well. First and foremost, I'll stress the use of visuals as nothing else has quite the same impact. There are a few ways to accomplish this. If it's possible, it's great to take people through collection spaces and have them experience for themselves how warm it gets because you have no cooling capabilities, or that 70% humidity can feel really damp. This is when you do want to point out those crumbling yellow pages or the channeling on the film that's making it increasingly hard to read, and discuss the steps you'd like to take to prevent this from continuing. When you do notice damage to your own collection, be sure to document it too. There's also the use of metrics, so I'm not going to go too much into this, but just briefly, the software that IPI uses, eClimate Notebook, has built-in preservation metrics The graph here shows the time-weighted preservation index, which is a quantification of that natural aging or that chemical deterioration, and is meant to give you a sense of how good an environment is from a preservation perspective of that. So you can use it to compare collection spaces across a institution, or use it to set your own benchmarks, or even just to see any improvements that have been made and what their difference would be on preservation. Another way that can be helpful in making the case to others, especially administrators, is to point out how preservation is related to your institution's mission statement. Sometimes this is more clear than others, but if you're part of a university, be sure to highlight instances where classes make use of the collections and keep records of requests for use by researchers. Additionally, outreach is often a core value, so engaging the public or having related groups advocate for at least portions of the collection can be useful. If you have a large textile collection, be sure to connect with the local quilters group or military reenactors and have them talk about why these materials are important to them. If you collect visitor feedback from exhibits, sometimes these include statements about how a particular object impacted someone. All this can help to show the collection's relevance to achieving institutional goals and making the case for caring for them. Relatedly, you may be able to speak to how such care is tied to your profession's or the institution's ethics. In addition to the moral appeal, often proving such things as having collections policies and demonstrating commitment to preservation are key to gaining official accreditation, respect and loans from other institutions, and grants to support institutional activities. Okay, finally, and we touched on this a bit before, but one thing that can also support buy-in is cost. Preventive actions are often far less expensive in the long run, not to mention better publicity. So the cost of pest traps compared to having a collection of tapestries mended after moths chew holes in them, or the cost of foam comparing to hiring a conservator to repair a ceramic. There are also published accounts by a few institutions that have reported on things like the costs of mold remediation, which can help to give a sense of the price tag of not addressing these environmental concerns. This is especially true once we start to incorporate sustainability. Often improving preservation can go hand in hand with running systems more efficiently and less costly. A good example is reducing the amount of time that lights are on when they're not needed. Not only does it lessen the exposure and potential for damage to objects, but it reduces lowers the electric bill and reduces the amount of heat that has to be removed from the space. And finally, it allows for prioritization of upgrades to spaces and HVAC systems by informing and helping to inform the financial perspective from that. Some of the other challenges that were noted in the registration survey cited dedicated funding. Hopefully some of the approaches we discussed today will help you to advocate for a permanent or larger collections care budget. But if not, there's a few other approaches to take. First of all, know that you can always grow. So if you can only afford a few data loggers at a time, that's absolutely fine. Help beginning the process, getting the data, becoming familiar with environmental management, and making it a part of the institution's daily life is a great step. And we can always add data loggers as we need to down the road, or use spot instruments until that time comes. In the US, you can also look into federal programs like NEH's Preservation Assistance Grants. Those were just, another round was just awarded yesterday, so congratulations to all of those who might have received them. There can also be regional ones provided by organizations such as the Greater Hudson Heritage Network, and sometimes your local ESCO, which is your energy supplying company, might have grants available to help with energy savings as well. For other countries, I believe the Canadian Conservation Institute loans instruments for taking spot measurements. I don't know if others are familiar with similar resources in other locations, but please share if you do. If staff time is one of the challenges, we can also make the argument that by sharing these responsibilities and bringing them up on a routine basis and addressing things early on, we will ultimately be spending less time on repeated issues or on things that have become bigger issues than they might have otherwise been. And for those of you who cited other as the main challenge to implementing a program, we would encourage you to reach out and we can try to brainstorm some ideas about how we might address those. So in conclusion, we've looked at how the building, the mechanical system, and the equipment in the space, as well as the layout of all of these things, can give us a sense of the tools and limitations available to us for creating our environment. We've talked about how extremes and microclimates can be a good approach to both preservation and sustainability, and how the local climate, the building envelope, and the mechanical system's capabilities can be analyzed through data analysis. We've looked at different levels and methods of control and talked about how teamwork can be used to begin evaluating our options. And we've talked about how to start, including some of the ways to overcome challenges and some of the pitfalls of things that we've seen not to do as well. So thank you all very much for attending. At this point, we'll be taking questions. I also want to once again emphasize that we really appreciate everyone who completed the post-webinar survey last time. If you wouldn't mind doing so this time as well, it's very helpful to us. This should appear when you close out of the webinar or be emailed to you in a link by tomorrow. And here again is the web address for the IPI sustainability page. Not only will you find a recording of today's webinar along with a PDF of the slides, but there's also a resources tab where the methodology book as well as the sustaining preservation practices book is located if you're interested in delving into any of these topics further. So thank you very much. Okay, so we're gonna, we don't have any questions at the moment, so we're gonna give it just a few minutes and then we'll be ending the webinar. Okay, so I think one of the questions we have here is how or where do you measure the outside climate? There's a number of options available to you. One of the easiest ways to do this is to install a data logger somewhere in the outside climate local to you. Most loggers, you're gonna wanna make sure they're placed in an area where there's where they're kind of protected from the rain and everything, because you don't want those to mess with that. Also, if you are using eClimate Notebook, there are ways to add the outside climate. We get our information from NOAA, and so it's updated regularly, and you can trend it over long periods of time. So I would, depending on where you are in the world, there may be other weather reporting services where you can get that outside climate, but if not, one of the best ways to do it, and especially because those are pulled from local airports, so if you really want to get a sense of what the climate is at your exact location, is to really have a data logger somewhere close to where your institution is. Okay.
So one of the other questions we have was to explain the deadband, what we mean when we say the deadband for a unit. The deadband tends to be, if you're aiming for, say, 70 degrees in a collection, the deadband would be you have 5 degrees to 75 or to 65 where the air can drift to. So if in the winter it can drift down to 65 before the air handling unit will come on and bring it back, or in the summertime it could drift up to 75 before the air handling unit will come and bring it back. One of the major reasons we're very hesitant is not only for the RH drift that Kelly had mentioned earlier, but there are times when we have seen people go 5 degrees is great, but I'm going to be more energy efficient. I want to go 8 to 10, and that brings even greater RH swings with it when that gets attempted. Another question is, what inexpensive data loggers would we recommend for a small museum? I mean, off the top of my head, there's a fair number of data loggers out there. A quick internet research would help bring a few up. One of the two connecting to collections care has a chart, the comparison chart to look at. I can say the ones we have experience with, there are hobos out there that about $125, I think they run. You have to double check with their site, but they are Bluetooth and a fairly reliable logger for the cost that you pay for it. Sorry, we're just going through some other.
Okay, one of the other questions we had here was to elaborate a bit on TWPI. So that's the time-weighted preservation index. And essentially what it is, I don't know if you recall from the graph here, I'll try to go back here, but you can see how there's peaks. So preservation is higher in the winter and then kind of drops in the summer because we have those higher temperatures and higher levels of relative humidity. So what the time-weighted preservation index is, it's based on experiments done with brand new rolls of acetate film and put in different combinations of temperature and relative humidity to see how long it was before noticeable deterioration occurred. So the reason it's time weighted is because we can never stop deterioration. So it only accelerates. So it's similar to if you have a carton of milk, if you put it in the fridge, it's going to last for a certain length of time. If you take it out and put it on the counter, it's going to last for significantly less. And if you switch back and forth between the counter and the fridge, it's not exactly half the time that it would have lasted in the fridge. It's going to be shorter because that time spent on that counter at the higher temperatures is just going to increase its curdling and deteriorate faster. So that's essentially what the TWPI is. It's a way to kind of account for how our environments change over the course of time. We don't often maintain exactly stable temperature and relative humidity over the course of a year, and so it's a way to account for those changes. Okay, and finally we had a question about why worry about relative humidity in winter and dew point in summer. So we'll touch on this a little bit. Dew point is, like I said, it's one of the factors that kind of controls the other two, but dew point is what's going to indicate when that dehumidification has to occur. Relative humidity we look at more in winter because when we start to see low relative humidity levels within a collection space, that's when we start to look at humidification. So it really has to do with part of the reason we look at the parameters differently on a seasonal basis has to do with what type of control we're going to be employing, if it's going to be dehumidification or humidification.
So we have another question that says, how many degrees does one person in a space increase the heat load? And should lowering the temperature during the work periods in relationship to this occur? So really the how many degrees does a person add is a tough question. There is, when we're taking my HVAC training, they give you an answer, but having seen data that we pulled from collection spaces, we see offices open up and you can actually see in the data when we pull it, probably about 3 degrees increase in some circumstances. And that's both the load from the exterior of the sun and whatnot, lighting load in the space and a person. So in general, it's probably a degree. In some major libraries, like really large occupancy, we've seen it gone up probably about 2 or 3 degrees when people start coming in. It's not hugely significant a person being in the space. So it wouldn't recommend lowering the temperature during the periods. What we would recommend, especially if you have an occupied collection space, if possible, is lowering it after hours to try and gain when there's no staff, if it's possible, when there's no staff member there, to get some gain in the preservation environment just after hours when no one's there, and even reduce some of the energy consumption during that period as well. From my past experience as a facility manager, the minute you start lowering the temperature whilst people are in the building, you will wind up having a significant number of complaints from people too cold or not liking changes that are made, and you'll wind up increasing your number of complaints. And lastly, if I have climate control, is it really bad to have more than 5-degree fluctuations? Someone said that once that it should be not more than one. We would say, I think our take would be 5 might be our limit of the most we'd want to see it go to. We wouldn't want to see it exceed that.
Yeah, and I would add to that that a lot of it's going to depend on what collection materials you have present, and where that 5 degrees is occurring within your temperature band. You know, if it's a 5-degree jump from 80 to 85 versus, you know, maybe occurring at lower temperatures, the level of deterioration that your collections are in. For example, film, the more deteriorated it is, the more important it is to have it in colder environments. So for materials like that, having you know, larger fluctuations that they can equilibrate to would cause a concern. So for fluctuations, like I said, it's going to matter a lot on the material as well as the condition of the material. It's also going to depend on you know, what your space is experiencing on a regular basis. You know, some people might regularly have swings, and how long those fluctuations are going to last. So if it's not long enough that, you know, if all the objects are within boxes within storage cabinets and data loggers within that don't show the same degree of fluctuation as within the room, it might be less of a concern. So I'd say we also have a question about more than a 5-degree shift in relative humidity over 24 hours, and if that is still a recommendation. Again, I think this ties in nicely to the previous question, but a lot of it, again, is going to depend on what standards and environmental parameters you've set for yourself and for your institution based on the needs of your collection and what your mechanical systems are capable of. So I would also add that setting those parameters and things like that are topics that we'll address to an even greater extent in the second series that's going to be beginning in January. So we would encourage everyone to tune into that as well. So I think there's, okay, one final question, and then I think we're going to go ahead and end the webinar. If we were to lower the temperature after spaces for an occupied collection space, would you do so only within a 5-degree band?
Our main goal with the dead band, when they recommend that, is to set that up so it occurs all day long. So over the day it'll fluctuate. It can fluctuate back and forth, and we wanted to try to reduce that as much as possible. What we recommend in reducing the temperature overnight is instead of running it like say 72 during the day when no staff are present, is reducing the temperature, not increasing a dead band, but just reducing the temperature overall for the space and not giving it more of a fluctuation.
Okay, well, thank you everyone for attending. And if there are any additional questions come up, please feel free to reach out. The recording of today's webinar as well as the PowerPoint should be available shortly. So we encourage you to visit the website for that. Thank you all again.